Welcome everyone to another session of our new young session within our Machine Learning Needs Mathematical Optimization seminar series. Very pleased to be back with another session and also see so many participants. So as always, we're going to have three speakers, but all the questions will be asked after all three speakers have made their presentations. So our first speaker is Farzaneh Pourahmadi, and she's a postdoctoral researcher at the Technical University of Denmark, DTU, and she's going to talk about explainable data-driven warm start for generation scheduling. So all yours, Farzaneh.
Thanks, Yasana, for the introduction, and thanks for having me. Let me share my screen. Can you see my screen?
Yes.
Perfect. Yes, so it's my pleasure to present our recent work on data-driven warm start for accelerating generation scheduling. This is a joint work with Jalal Kazempour from Technical University of Denmark. Let me first start by giving you the motivation behind this work. All we know that a large number of real-world decision-making problems can be modeled as mixed integer optimization. And these problems come from different areas, from computer science, operation research, economics, and energy systems. And in this talk, we will focus on one specific application of mixed integer optimization to energy systems. But the issue about mixed integer optimization is that the capacity of the mixed integer optimization solvers, although it has increased at a rate of over 1 trillion times in the previous years, but it's still more computationally difficult to solve this problem compared to convex optimization. And especially when we have larger scale problem and when we have time limitation for our decision making, it's very difficult to solve. Now I'm focusing on one of the most fundamental mixed integer optimization problems in power systems and electricity markets, which is called generation scheduling or unit commitment. In this problem, we would like to find the most cost-efficient schedule for power generating units. And to do so, we typically model this problem as a mixed integer program, where the output of this optimization model is our decision variables, including on and off commitment status of generating units and also the power production of these units. And the input of this optimization model is our parameters like consumption and the production of renewables and the parameters of our network. And if we are in the electricity market setting, also the bits of market participants. In order to model generation scheduling problem, we can write our optimization as in this form, that we want to minimize our cost, which includes production cost, startup cost, fixed cost of generating units, subject to various types of constraints, operational, physical, and economic constraints. The size of this problem obviously depends on the number of generating units and discrete time periods, and also the uncertainty scenario that we would like to model. So we can say that the number of variables and constraints depends on this number of units and this time periods, and also the scenarios that we would like to include, which may reach to the order of thousands or even millions. So from optimization perspective, this problem for real test systems can be computationally difficult to solve. There are two main determinants for this complexity. First, because of the binary nature of some decisions, for example, which generating units should be on or which generating units should be off. So we have binary variables, which makes our problem non-convex. And also another issue is that we have to model the complex physical laws of transmission networks, which add nonlinear and even non-convex constraints into our problem. And also this complexity is getting worse as we add more renewables, because we will add high degree of uncertainty, and this needs resolving these models at much faster paces, which is not reachable by the state-of-the-art solvers. And at the end, it will result in a solution with high optimality gap. A good thing about generation scheduling problem is that we solve these problems over and over again, at least once a day or even multiple times a day. So there is, and also for this problem, we don't change the topology of our network very often. And also, for example, for our parameters like consumption, most of the times it is resembling to what happened in the previous days. So it means that we repeatedly solve similar problems. So there is a great opportunity for using machine learning here. And by learning from previous schedules, from previous instances, there is a great potential for reducing this complexity and improve the computational performance. So this is what is motivating us to use machine learning for generation scheduling problem. In this work, we would like to answer these three research questions. First, how can we effectively extract information from our previous problems to improve the computational performance? And when we say, okay, we improve the computational performance, so the next question is that to what extent we can improve this, we can enhance this efficiency. And when we improve this computational performance, what is the potential cost reduction when we use machine learning? So these are these three research questions that in the following we would like to answer. And this is the outline of my talk. First, I'll move on to the research gap and the challenges that we have for using machine learning for energy systems, and what is our proposed framework to solve these issues, and to demonstrate the efficiency of our proposed framework, I'll show you some numerical results. So when we look at the literature review, there are two main directions for using machine learning for optimization. The first direction is that we try to train a machine learning model which maps the output of optimization model to its input. So it means that we want to estimate a mapping function which maps the input to the output. But you know, using machine learning in energy systems is different from like using machine learning in computer vision. Let's say, for example, we have an image and we would like to learn these images. So in this application, we don't have specific constraints. But in energy systems, we have lots of physical and engineering constraints. And this is a challenge for machine learning because the output of this machine learning cannot guarantee that we can satisfy these constraints. Another direction is that we try to combine machine learning and mathematical optimization. So what we are trying to do here is that we would like to do the things that machine learning and optimization cannot achieve independently. But by putting them together, we can achieve them. So for example, here to achieve the feasibility and optimality of our decision, so we can combine these two. So actually, our proposed framework is based on the second direction. And as you can see here, so this is our previous mixed integer program, right? So we try to train a classification machine learning model here to predict our decision. So our input is again the parameters of our model, and we want to predict, for example, the on and off commitment status of generating units, and use it as a warm start to the solver of our mixed integer program. So obviously the runtime reduction that we can have here is highly dependent on the quality of this warm start. So better warm start will result in a better computational performance. So in this work, we would like to focus on this learning part and see how we can enhance the quality of this warm start. This is the framework of the pipeline of our machine learning model classification. So in the first step, we try to collect our data, and then we train the classifier and use it for prediction, and then we use it as a warm start, and at the end we evaluate the whole framework. Okay, first part, data preparation. So for data preparation, let's get back to the optimization model. So let's say that our input is zeta, which is the parameters like consumption, renewable production, and so on. And the output of this optimization model is the optimal value of binary variables, and we denote it by S of zeta. So here we want to determine the number of samples that we require for our training. So for that, we use this probability theory, saying that if we have n number of samples, and if n1 is the number of outputs that appeared exactly once, we can guarantee that the probability of observing a new output will be less than this specific threshold. So with respect to the desired threshold that we would like to have, we can obtain this number of samples, right? So we collect our data set and the samples and build the training data set. And then we want to train a classifier to predict the binary variables. So for simplicity, for each binary variable, we do binary classification. That this binary classification can be linear classification or nonlinear classification. So yeah, as you can see here, for classical machine learning model, we would like to minimize the expectation of our misclassification in expectation. Yeah, we would like to minimize it in expectation. To improve our classification model, we use two techniques. First, we use the kernel tricks to extend the linear classification to nonlinear space, and also we use regularization to avoid overfitting for our classification. But you know, in a classical machine learning model, we usually assume that the distribution of test data set is similar to the distribution of training data set, which is not the case in practice, right? So here we use the context of distributional robust optimization for our regularization to robustify our prediction against the changes that we can have for our distribution. And yes, so this is the second technique that we use. And how we can evaluate the performance. Here, as I told you, we first use the classifier to predict binary variables and use it as a warm start for our decision making. So when we look at this framework, in perspective of, from perspective of objective function, for the prediction, we would like to minimize the prediction error. We would like to maximize the accuracy. For decision making part, we would like to minimize the cost or maximize the revenue. And these two objective functions are not necessarily aligned, right? So how we can evaluate the whole framework? So we consider two scenarios here. So in the first scenario, we assume that, okay, if we don't have any time limitation for our problem, what is the fastest possible time to obtain the optimal solution when we use a machine learning model? And in the second scenario, we assume that if we have a time constraint, what is the minimum optimality gap we can achieve? So we implement this framework on these test systems, IEEE 118 bus test systems. So in this test system, in summary, we have this number of binary variables, which is higher than 13,000. And this is the number of constraints. It's more than 55,000. So this constraints also includes both linear and second order core constraints. But because we have binaries, our problem is not convex. But here we focus on deterministic mixed integer second order core program. So we implement our proposed framework, and we consider, as I told you, two scenarios to evaluate it. So in the left figure, we assume that we don't have any time limitation. So at the end, for each warm start, for example, the first one is that we don't have any warm start. This is the classical linear classification. And this is the classification that we use both kernel function and regularization. Yes. And then we see that, yes, so our approach works better than the original optimization model. And in the case that we have time limitation, we can see that we have a huge cost saving. So to conclude, we propose a framework based on machine learning model to transfer the computational burdens from online to offline. And we show that there is a trade-off between the solution quality and runtime reduction. Yes, and we observed that the kernelized support vector machine with regularization works very well. Thank you for your attention, and I will be happy to take your question at the end of the session. Thank you.
Thank you so much. That was a really nice presentation. So we'll continue with our second speaker. Our second speaker is Brais González Rodríguez. He's a postdoctoral researcher at Ivey Business School, and he's going to talk about learning for spatial branching and algorithm selection approach. So, all yours.
Okay, thank you. Let me share the screen. Okay. Can you see the slides now?
Yes, I can see them.
Okay. Okay, so hello everyone, and thank you for being here today, and thanks also to the organizers for inviting me to this session. My name is Brais, and I am now doing a postdoc at Ivey Business School. However, the work I will present today was carried out when I was doing my PhD thesis at the University of Santiago de Compostela and the Galician Center for Mathematical Research and Technology. And this talk is about the use of machine learning in order to improve the performance of a branch and bounds algorithm in the context of polynomial optimization. So this work is based on the following paper, already published in Infor's Journal on Computing and co-authored by Bisan, Ignacio, Julio, Bea, and Sofia. Well, the main objectives of this work are the following ones. First, to define some features associated to a given polynomial optimization problem, which are useful for the learning process. Second, to define a new portfolio of branching rules in a branch and bounds algorithm. Also to define a new key performance indicator, a KPI, to measure the performance of the algorithm, to present a learning framework to learn the best branching rule for a given polynomial optimization problem, and finally to show some computational results of that learning. So first of all, I need to introduce the algorithm we use to solve polynomial optimization problems. This algorithm is based on the well-known reformulation linearization technique introduced by Sherali and Tanguilek. So first, we define a polynomial optimization problem as follows, where phi r are polynomials. We also consider a hyperrectangle omega, like this one. So all variables are bounded and they are greater than or equal to 0. For this work, we consider only problems with continuous variables. And now we have to define some ingredients. So first, the RLT variables. We defined one new RLT variable for each monomial of degree greater than 1. So for example, for the monomial x1 multiplied by x2, we define the new RLT variable, capital X1, 1, 2. We also need to define the bound factor inequalities, which are given by the expressions here. A variable minus its lower bound greater than or equal to 0, and an upper bound minus the corresponding variable greater than or equal to 0. And finally, we define the bound factor constraints, which are given by the product of the bound factor inequalities delta times, where delta is the degree of the problem. Good, so the RLT algorithm is based on solving linear realizations of the original polynomial optimization problem. So now I'm going to explain how we build these relaxations. So first, we'll consider the original polynomial optimization problem. Now we have to add the bound factor constraints. Next step is to linearize all the polynomials. So we replace all the monomials of degree greater than 1 with the corresponding RLT variable. Now, if we added the RLT identities, we would have a problem equivalent to the original one, but they are nonlinear and they are not part of the relaxation. And finally, we use a branch and bound algorithm leaning on an auxiliary linear solver. Well, now with all these ingredients, we can define the branching rule used in the branch and bounds algorithm. In the original paper of Sherali and Tanguilek, they use the following branching rule based on the violations of the RLT identities is here. So for each variable, they consider all the monomials in which this variable appears, and they compute the maximum of the violations in this way. So the branching variable is then the variable with the highest value of this theta. In a more recent paper, they propose to replace that maximum by a sum of the violations, improving the performance of the algorithm. And our approach is to maintain the use of this sum of violations, but giving some weights to the violations. So we defined these new weights in different forms. So first one is considering all of them equal to 1. That is the standard branching rule. Second one is to define the weights as the sum of the absolute values of the coefficients of the associated monomial. Another approach is to use the dual values of the constraints in which the corresponding monomial appears. We can also consider how much the range of the corresponding variable was reduced since the beginning of the algorithm. And finally, we can use the density of the variable to prioritize the variables with a higher density in the branch and bound process. Well, an important question is, does the algorithm still converge to a global optimum of the problem if we modify the branching rule? Well, the following theorem ensures that the convergence of the algorithm is guaranteed if the weights are greater than 0. A proof of this theorem can be found in my PhD thesis, Advances in Polynomial Optimization. And now, regarding the computational experiments, I will present. They are based on the following paper published on Journal of Global Optimization. And in this paper, we present our own implementation of the RLT algorithm called Raposa, and we also study the performance of the different branching rules presented in the previous slide, along with other enhancements of the technique. So the instant used on that work are the same we use in this work, and they are the following ones. First one, taken from Dalkiran and Sherali, consists of randomly generated problems from degree 2 to degree 7 with different densities. Second one is the well-known NLP library, which contains instances from papers based on real problems. And finally, QP library, which consists of quadratic problems of diverse nature. One of the main contributions of this work is the use of some graph-based features to improve the learning process. So we consider two graphs associated to a given polynomial optimization problem. The first one is the variable intersection graph. So given a polynomial optimization problem, we define a graph with n nodes, where n is the number of variables, and we add an edge between two nodes if the corresponding variables appear together in the same monomial. We also define a new graph. We call it a constraints monomial intersection graph, which has m plus m nodes, where n is the number of variables and m is the number of constraints. So now we add an edge between a node associated to a variable and a node associated to a constraint if the variable appears in that constraint. Well, with these graphs, we consider popular graph measures as input features for our machine learning technique. And some of them are the density, the agent centrality, tree width, modularity, transitivity, and finally the agent centrality. So using these graphs, we also define two new branching rules using this agent centrality of a given variable as the weight in the branching rule formula. No, sorry. Let me go back. Okay, now. So now we define a new key performance indicator, KPI, to measure the performance of the different branching rules. We call it pace, and it is defined as follows: the time it takes to increase the lower bound of the algorithm by 1 unit. And we add here an epsilon to avoid division by 0. Well, the first question could be why we use the lower bound and not the optimality gap. Well, that is good point. So we have seen that changes in the branching rule have an impact in how fast the lower bound increases, and not so much in the upper bound. Moreover, we have a lower bound when the algorithm starts, just by solving the first linear relaxation. However, we do not have an upper bound at the beginning of the algorithm, so we cannot compute the optimality gap at the root node. We also define the normalized space, whose value is always between 0 and 1, being 1 the best performance. To do this, we simply get the best space, that is the lowest, and divide it by the pace of the corresponding branching criterion. But why is important to use a measure like this? Well, in the literature, people usually use the running time of the algorithm or the optimality gap returned by the algorithm. So in our set of instances, we have some easy instances solved in the time limit, and we have other instances which are not solved in the time limit. So for the first ones, running time is a good measure of performance. And for the second one, optimality gap is the way of measure the performance since the time limit was reached. So the strong point of the pace is that it can be used for all instances, regardless of if they were solved in time or not. So with all these ingredients, the first question is how good is our portfolio of branching rules? Well, in this work, we consider the 5 branching rules which give the best performance and the original one. So we have here in the legend the maximum of the violations, the sum of the violations, and the weights given by the dual values, the range of the variable, the agent centrality of the variable intersection graph, and the agent centrality of the constraint monomial intersection graph. So in this figure, we can see for each battery the percentage of the instances in which each branching rule gave the best performance. So, for example, for the branching rule based on the range of variables, we can see that it performs so good in the first 2 sets of instances, but worse in the last one. We can see something similar for the rule based on the centrality of the constraint monomial intersection graph. So we have variability between the rules, which is a good indicator that a machine learning technique can be useful to improve the performance. Here now in these box plots, we can see the normalized pace for each branching rule on each set of instances. Remember that closer than 1, better the performance. So we can see again that the rule based on the range of the variables here performs very good in one battery, but very bad in another one. And similar for the agent centrality, as we see in the previous slide. So, well, question is there anything to learn? Well, in this table, we can see in the first row the geometric mean of the pace if we consider the best branching rule along all the instances, which in this case is the one based on the range of the variables. Here in the second row, the optimal rule, we can see the geometric mean of the pace if we choose on each instance the rule with the best performance on that instance. That is the best performance a machine learning technique can deliver, assuming that it always chooses the best branching rule. So we have that we can improve the performance of the algorithm in about 43%. So what is let's say, the objective of the learning? Well, the ideal objective is to have like a crystal ball and be able to predict for a given instance the branching rule with the best performance. And what do we have to do this? Yeah, we have about 35 features for each instance, and we have the data of the performance of each branching criterion on each instance. And the way we did the learning process was using quantile regression, since theoretically it fit well with our data, because we have some outliers. However, we also did the learning with linear regression, and the results were quite similar. We also tried different types of quantile regression, quantile generalized adaptive models, boosting for quantile regression, and also quantile random forest. So yeah, regarding the results, doing this, we obtained these results here. So we split our set of instances in training and test set, 70% and 30%. And we did this 10 times randomly. The results on the table are the average of the geometric mean of the pays in these 10 experiments.
1 minute, Brais.
Okay, thank you. Yeah, we can see that with the machine learning based rule, we improve the performance of the algorithm in about 23-25%, more or less, when the maximum we could improve is 36. Moreover, the results are very similar regardless of the statistical technique chosen to do the corresponding regressions. And finally, we have here the same box plots as in previous slides, but now we have added the first box plot for the machine learning based branching rule here in red. So if we look at all the instances together in these first box plots, the performance of the machine learning rule looks pretty nice. Looking at this figure, we can also see that the machine learning chooses the branching rules in a similar proportion in which they are the best ones. And finally, some conclusions on future work. When we have presented new graph-based features for a given polynomial optimization problem, we have introduced a new key performance indicator to measure the performance of the algorithm. We have presented a framework for learning rules in spatial branching. We also have shown in different numerical experiments that the resulting gains in performance can be significant. And well, moreover, we also have another work under review in which we use this methodology in another part of the algorithm, and the results are also good. And now we are working in using node-by-node features to learn the optimal branching rule at each node, instead of selecting one for every node of each instance. Yeah, this is all from my side, so thank you all for your attention.
Thank you very much, Brais. That was a really interesting presentation. So we're going to finish with Jiachang Liu. He's a PhD candidate at Duke University, and he's going to talk about FasterRisk, fast and accurate interpretable risk scores. All yours.
Thank you very much for the introduction. Can you see the slides?
Right now, yeah, no? I can see them.
Okay. Hello, everyone. My name is Jiachang Liu. I'm a PhD student at Duke University. So today I will present to you about our recent work called FasterRisk, Fast and Accurate Interpretable Risk Scores. This is joint work with Chuli Zhong, Boxuan Li, and Cynthia Rudin and Duke, and also Margot Selzer and the University of British Columbia. So to start, let me give you some background. What is a risk score? So below, I'm presenting to you a table with several features and some integer numbers. So using this table, first of all, is trained on the mammal data set to predict the malignant breast lesions for breast cancer prediction purposes. So using this table, if a patient comes to the hospital, the nurse can use this table quickly to do a triage on the patient just by going through each patient. If the image has some kind of oval shape, then we can subtract 2 points from the patient. If the age of the patient is greater than or equal to 60, then we can add 3 points. At the end, we will get a total score. And next, using this total score, we can go to the table below to convert this score into a probability or risk. This will tell us how likely the patient will get breast cancer. Such a system in total together is what we call a scoring system or risk score. So why do we want to study scoring systems? First of all, it's very easy to use and it's highly interpretable. All the, as you can see, all the numbers here are very small integers, so people can just quickly calculate the total scores in his or her mind right on the spot. It doesn't need any calculators at all. Second of all, it has already been widely deployed, especially in medical care system. So this is a screenshot from Wikipedia, and there are many scoring systems that have been invented in the past. Just to give you some example, this one Aldrich scoring system here is used to discharge patients from post-anesthesia. And here's another one, and it's used to predict prognosis and mortality rates of acute pancreatitis. Lastly, here's a famous Framingham study, and it has been used to estimate the 10-year cardiovascular risk of an individual. So many scoring systems have been invented, but usually these systems are invented by people based on their past experiences. But we want to ask the question, are these systems accurate enough? Do there exist more accurate models? If there exist, how can we find them? This is a very important question, because if we can find more accurate models, then it will have a dramatic impact on people's life, and we could potentially save many more lives. However, to design such an optimal or very high accurate risk score is very challenging. There are a few key challenges. The first one is obviously accuracy. We want to find a model that performs better than existing models. Second of all, we're imposing a sparsity constraint because we want the model to be very small so that it's interpretable to practitioners. Lastly, we are restricting all the coefficients to be integers because it will reduce the computational burden for the people to use them. So just to briefly talk about the past approaches people have done, the first one obviously is that the expert can design the model by itself without using any data, just based on the past experiences. The second one is to naively train a logistic regression model and just run the coefficient to integers based on the thresholds at 0.5. However, I'm giving you an example here. We're using 5 features. If we train them and we do naive rounding, then we are ignoring 3 features. So the model below with just 2 features could potentially have less predictive power than the model before. So naive rounding wouldn't work very well in practice either. Recently, there has been some work try to use a MIP solver to solve the problem by formulating the whole problem as a mixed integer programming problem and try to solve them through branch and bound and counting planes. However, the drawback of this method is that usually a commercial MIP solver is required. However, it's very expensive, so it's not very easy to deploy them in large healthcare systems in a whole nation. And it runs computationally very slow. So our objective or our goal is to quickly produce near optimal solutions. Before I dive into the details of the algorithms, I just want to show you an additional result to let you guys have a better idea what our algorithm is capable of. So this scoring system here is trained on the FICO dataset, and it's used to predict whether an individual will default on a loan or not. So a financial company can use such a model to decide whether to give the credit or the loan to the applicant. So this model, you can see here, the data is very huge. It has 1917 binary features and has approximately 10,000 samples. After training, we can just extract 5 features, and the performance is very well. It outperforms all the existing risk scoring algorithms, and it's also on par with the existing black box models. So it's very convenient to use and it performs very well. Additionally, the training time is only 13 seconds to train that. And the bonus of our algorithm, lastly, is that we can return many scores, many scoring systems for the experts to inspect and discuss with each other, so they can pick the best one out of them and deploy it in the real world. And lastly, our code is open source and is free to use, so it doesn't require any commercial MIP solver license. Lastly, I just want to talk about why do we need fast computational speed in this case, if the MIP-based method can give us already accurate prediction. So as a PhD student, most of the time, I have been focused on developing data mining algorithms. However, from a data science perspective, in practice, the whole data science process is much bigger than data mining. It also includes data selection, pre-processing, transformation, and evaluation. And at any stage in this process, we are allowed to go back and redo some of the steps in order to improve the final performance. And usually the other boring steps like pre-processing or transformation, they lead to dramatic improvement for the final result. So if we can improve the algorithm speed during data mining, then the practitioners can go through these iterations many more times, and hopefully after doing this several rounds of times, they can improve the performance better. So we are intentionally trying to come up with fast speed in order for practitioners to use them more conveniently. So now let's dive into the details of the algorithms. As any optimization problem, we first want to define the objective function, which is a logistic loss, and then we also impose several constraints. The first constraint is sparsity constraint. We want the model to be sparse. And second of all, we're restricting all the coefficients to be integers. And lastly, we're restricting all the coefficients to be -5 and 5. So essentially, we're putting a box constraint. We're restricting the coefficient to be in a small interval because having a large coefficient will add the extra computational burden for the person to use them. So we're intentionally trying to select small integers. So how are we going to solve such a complicated problem? It's obviously NP hard to solve them. So we're solving this problem through three steps. The first one is that we want to solve the problem by finding sparse continuous solutions using beam search. And this beam search idea is borrowed from the NLP, natural language processing literature. Just to give you guys a concrete example, suppose we want to find the 3 best features out of a total of 5 features. So we start from an empty support, and during each iteration, we try to select one coordinate at a time and add into our support. And each time when we add a coordinate into our support, we try to find the feature that if we optimize the coefficient, it would lead to the largest decrease of our total logistic loss. And we through this step by step to add more and more features until at the end we find the best solutions. And in this step, all the coefficients are continuous. And the second step, we actually for many data sets, when we're trying to find sparse model, there exist many sparse models that perform equally well, and we want to capture these models. And to do this, we are going to do something called swapping. So we try to delete one feature in our support in the solution we find from step 1, and trying to find an alternative feature that would also lead to a good, a tolerable loss defined by some tolerance level. So if the new support, once we try to fine tune and optimize the coefficients on the new support, the loss is less or equal to some 1 plus epsilon threshold, then we add that solution into our solution pool. And the collection of all these sparse solutions is something called a Rashomon set. So lastly, for all the continuous sparse solutions we find through step 1 and step 2, we try to round all the coefficients into integers. But before we do rounding, we further step called scaling. We use some multiplier and multiply all the coefficients by a constant. So suppose our W is given starting with a bias equal to 0.5. We use a multiplier equal to 2.225 and multiply everything. And then we get a new coefficient solution. And we try to round this new coefficient one coordinate at a time using either rounding up or rounding down in order to get the final integer solutions. I'm just giving you an example here. However, it's a little bit more nuanced and complicated. In our paper, we actually present a theorem telling us, which order we should go through to round the coefficient and whether we should round up or round down. So the ordering and also the rounding operation is not arbitrary. It's actually determined by the theorem in our paper. So through these steps, we're able to produce many good solutions from our algorithms. So here is an example to show you we can find many solutions from the MAMO dataset I showed you on slides 1. And they all have slightly different features, but the performance on the training and test dataset for the AUC is all greater than or equal to 0.852. So hopefully the practitioners can find one that best fits with their domain knowledge. Lastly, to give you some quantitative evaluation, on the left, I'm showing you the training AUC versus model size, and on the right, I'm showing you the test AUC versus model size. So our model is shown in red curve, and it performs better than all the existing algorithms out there. So the first one is on the adult data set, and we are also shown on the bank data set, MAMO, Mushroom, Compass, and FICO. So the trend is pretty consistent, and especially for the last two, the Compass and the FICO, the P, which stands for the number of features, is very large, and they're very highly correlated. And basically, our red curve, FasterRisk outperform everything, and also the standard error bars doesn't overlap each other. So the improvement is statistically significant. Here's another one, just throwing out all the other baselines, comparing with the MIP-based method, RISC-SLIM, and we are outperforming the MIP-based method on all the cases I'm showing you here. And lastly, to compare with computational speed with RISC-SLIM, the red bars are with our algorithm FasterRisk, and the blue bars are with RISC-SLIM, the MIP-based method, and we are much faster than the MIP-based method. And we are restricting the running time to be under 900 seconds or 15 minutes. And so the trend is pretty consistent throughout all the data set. And RISC-SLIM almost hits all the running data set when either N or P are very large. And we also extend the running time to be 1 hour in the appendix of our paper. And basically, the trend is the same, and the AUC actually doesn't improve that much for the MIP-based method. So in summary, I present to you guys a 3-step to how to create a sparse scoring system for our data set. And at the end, it will return all the highly accurate models within minutes. Thank you very much. So the paper is posted on arXiv. It's accepted into NeEDS 2022, and the code is also posted on GitHub. Finally, I just want to present to you the logo of our paper, which is the F star showing on the left. So our name of our algorithm is called FasterRisk. It can be decomposed as F asterisk, so that's why we have the logo F star. And hopefully you enjoyed the presentation, and I'm happy to answer any questions online or through emails. Thank you very much.
Thank you so much for the great presentation. We now open up for questions from the audience to any of the three speakers. If you have a question, please raise your hand or write in the chat, and we'll give you permission to use your microphone and camera. Okay, it seems like we don't. Oh, we have a question in the chat.
So the banking data set, I think we downloaded from the UCI repository, and it's also, I think I use it from the Rick Slim's repository. Let me find the link for you. So example data. So the link for all the data sets, I think partially Compass and FICO you have to apply in order to get the permission to use the data set. But other data set you should be able to find it through this link. And they did some pre-processing, so they convert to all the binary features. But you can find them either through UCI repository or through this GitHub page.
Thank you very much for the question. Any other questions? Please write in the chat or raise your hand. It seems we don't have any more questions. So once again, thank you very much to the three speakers. And we have a 2-week break for the online seminar series. So we are back on April 17th again with the regular seminar.
Thank you all. It was really nice.
Thank you.